Let's talk about trigonometry. Trigonometry for right angle triangles. This doesn't quite look like one. This is a right angle triangle that I'm trying for here. So I've got capital A, capital B, capital C as my angles, and then I have leg little a, leg little b, leg little c. This leg right here, if I'm talking about the angle A, this is my angle. This B leg here is the adjacent leg, and this is the leg opposite, and this of course is the hypotenuse. And in this right angle trigonometry that we've got going for us, we have this idea of ratios. And a ratio is just a fraction that creates some sort of relationship. And here's what I've got. We've got three relationships that we're going to talk about. We're going to talk about the sine relationship, the cosine relationship, and the tangent relationship. And for each of these relationships that we're talking about, these ratios, it's always happening on an angle, and here I'm talking about it happening with angle A. So of course if I was starting from angle B, then this one would be the adjacent leg, and the far one over here would be the opposite. So it would change depending on what angle you're talking about. Here we're talking about angle A, just because I have to pick one to discuss. The way we don't always want to write sine, cosine, and tangent A, so instead we tend to write sine A, cos A, and tan A. These sines, cosines, and tangents from our talk about functions earlier are functions, so I can put function parentheses if I want. Again, just like with exponents and logarithms, I tend to not put function parentheses. It's an acceptable shorthand to not do that. And for these three trig identities that we've got, again, maybe I tend to not do function parentheses. We've got these relationships that happen. I've got opposite over hypotenuse, I've got adjacent over hypotenuse, and I've got opposite over adjacent. Abbreviate opposite is OPP, adjacent is ADJ, and hypotenuse is HYP. Maybe in your book they would call this A over C, B over C, and finally A over B. But I think these ones make a little more sense, and they've got this way you remember it. So I have SOH for sine is opposite over hypotenuse, CAH for cosine is adjacent over hypotenuse, and then I have TOA for tangent is opposite over adjacent. So these are my three relationships. This is pronounced SOHCAHTOA, and your book has some phrase in it. Maybe some old hog came around here and took our apples. There's about 50,000 different ways to remember these three things to create this relationship. So this is the relationship I've got, and again, this opposite is a length. It's the length of the leg A, and then the hypotenuse, of course, again is a length. Because this is a right triangle, we also have this relationship, c squared equals a squared plus b squared. That Pythagorean theorem also stays true. And the main thing is that we can use these relationships and angles to find out information, particularly this. And here's what you've got. If you don't know what the angle A is, but you know the lengths, you can figure out what sine A is by creating this ratio. But the more powerful way of using this is if you actually are able to use something like maybe a protractor. Maybe you've seen a protractor before. It usually looks like this, and it has all the different angles written out on it from 0 degrees to 180 degrees, and then you can just measure what angle you see and figure out how many degrees it is. But if you actually know what the angle is, then there's a way to calculate what sine of that angle is, and then you can create this cool relationship and solve something. So let's talk about a word problem that lets me use trigonometry. It was the development of trigonometry coupled with the ability of using logs and exponents to solve large number problems that allowed sailing ships to successfully navigate the globe even and figure out where they were positioned. And GPS and our iPhones and whatnot is the same way today. If you use a GPS, I don't know, a TomTom or something, it uses trigonometry. And here's how you would use trigonometry to do this. Let's talk about some kind of spy situation. And maybe I'm from the era when we were all very much afraid that the Soviets were going to build something very, very scary. So we had the USSR in the height of the Cold War. And this was a big deal. So for my spy satellite footage, here's the picture that I've got. And what I've got here is some sort of building that's getting built. And this is the top of that building. And that's all I can see. My spy satellite's gone over, it's done that. I don't know, I see some little round things here that are trees. I don't know much about them. I see some steps. There's a sort of a path that goes up to the steps. There's a parking lot. I don't know if the Soviets had organized parking lots like we did. I think we were very afraid of us versus them. But I don't know. Here's some cars in my parking lots. I've got my cars and all this stuff. But the main thing that's going on is this. From my building, it's casting a shadow. And I know I'm doing the shadow in entirely the wrong color, but I don't have any better color to do a shadow. And so I see this shadow, and this is all I can see from my spy satellite. Other than this one last piece of information, I know that the time is 2:04 p.m. on the 13th of June. Because I knew that from my satellite had the time, the local time. This is what my satellite picture gives me. My big question, since I'm trying to spy on them, is to figure out how tall is this building. Once I know how tall this building and combine that with the number of cars parked there, I can figure out, is the correct number of people seeming to work in this building? You know, if the building's like super, super tall and they only have 20 people showing up in cars, then I might decide that it's a building that takes a lot of space. Maybe they're doing nuclear tests or something in there. So I start to wonder about things that are going on. That's what I see. Now, of course, although I see the top of this roof of my building, I know in real life how buildings work. They work something like this. Somewhere there's a door and all that good stuff. And when there is a shadow off to the side, I know it extends out like this. Here's what I know. Because I know the time of day and the day of the year, I can consult an almanac and find out what the angle of the sun's elevation is. So here's what I'm doing. I'm drawing this from a side. This side picture is not, of course, what my satellite gave me. It is simply what I know as a usual true fact. So here's my sun. I don't know. Let's have a happy sun. We are spying on the Russians after all. The sun is shining as bright as he knows how, and as the sun shines down, because I know the time of the day and the day of the year, I know what the angle of the sun's elevation is. And because I know that angle, I know how high up the sun is in the air. That means I know this angle right here. We call it the solar elevation. And I'm saying that this is going to be 45 degrees for this day of the year. Furthermore, because I know how you make car lots, I know what the usual distance is in between the lines in a car place. Because I know that usual distance, I can measure out how many of those distances my shadow goes, and that tells me that the length of my shadow is 25 feet. Now, I'm curious how tall my building is. So let's figure it out. Well, I need to figure out this side right here. This is what I'm shooting for. This is the side I'm after. In terms of my triangle with my sine and ratio things, what I'm trying to find is the opposite part. So I want the opposite. That's the part I don't know. I happen to know something about the adjacent. I know it's 25. So I need to go back up here to my trig formulas and see which one talks about opposites and adjacents. And that's going to be tangent. So here's what I've really got going. I know that tangent of angle A is opposite over adjacent. Now I start to plug in what I know. I know that tangent of 45 degrees is equal to opposite over adjacent, but adjacent was 25 feet. Now I go up here, I plug in 25 degrees into my calculator, make sure that it's on degrees. There are also other ways you can measure angles, including radians, but we're dealing with degrees. So it's 45 degrees that I've got going here, and then I hit the tangent. That tells me that tangent of 45 degrees is 1. So I know this left side is 1. 1 is equal to opposite over 25. And now I just do some algebra on this. This is now multiplication parentheses, so I can multiply both sides by 25. That lets me cancel out here on the right side. And that tells me that my final answer is that 25 feet is what my opposite side is in height. That means my building is 25 feet tall. Well, if the normal floor, I think, is 8 feet, 25 divided by 8 tells me that there's about 3 stories to my building. It's 3 stories tall, because it's 25 feet tall. If I count up the cars, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 cars. For a 3-story building. I know how tall my building is, I know how many cars there are, and again, because I was able to measure this common car distance here, and that's how I knew that my shadow was 25 feet, that tells me also, if I look at this roof, maybe it looks like the roof is 25 feet would be this long, and then there's just a little bit more right here. So I don't know, maybe this is a 35-foot long building on the height. I can know something about the roof. 35 feet long. I could figure out how wide the roof is. I don't know, maybe that looks almost like double this. So that's going to be 50. 35 by 50. Obviously my feet example thing here is very rough because that's not the main point I want you focusing on. I want you mainly focusing on this tangent process where I was able to, since I could use my calculator and call up what tangent of 45 degrees was, I could figure out that my building was going to be 25 feet tall. And that's actually how a spy satellite footage and stuff works. You figure out the angle of the sun's elevation, and then you can use trigonometry, and that lets you figure out how tall something is. And I think that pretty much wraps up what you can do in section 10.6. So go look in on the examples and maybe make sure that you play around with your calculator for some of the different sine, cosine, and tangents of some particular angles where you already know the answer to make sure you're getting the right input. Again, a big thing to memorize for your calculator is to make sure your calculator is in degree mode because we're using degrees.